We are continuing to learn about the chapter equilibrium. We're in the last but two topics left in this chapter. In the previous video, we had discussed the how we prepare buffer solutions, and we talked about Henderson-Hasselbalch equation. Feel free to check that out. As always, let me know if you found this video helpful and if you have any other questions as well. In this video, we are going to be discussing the solubility equilibria of sparingly soluble salts. Before that, we're going to talk about what are the important factors that affect the solubility of an ionic solid. Okay, so that's what we're going to do in this video. We're going to talk about two specific enthalpies, which is the lattice enthalpy and the solvation enthalpy. Okay, in the end of this video, you'll be able to understand, or you'll have a basic understanding of those concepts. So here you have two ionic solids, example, calcium chloride, CaCl2, and lithium fluoride. Calcium chloride is so soluble in water that if you leave it out in the atmosphere, it starts absorbing the water from the air. So it is hygroscopic in nature. What is that word called? It's hygroscopic. So it just absorbs the water from the atmosphere. On the other end of the spectrum, you have lithium fluoride, which is not at all soluble in water, so much so that it basically seems like it's insoluble. And then you have the others which are somewhere in between in terms of solubility in water. Okay, so there are two very important factors that we consider when we talk about solubility. One of them is lattice enthalpy, the second is the solvation enthalpy. And in your textbooks, they've just given you a basic overview of these two concepts. So the first one is lattice enthalpy. The lattice enthalpy is basically the measure of the strength of forces between the two ions. Okay, so for example, sodium chloride, that is salt, table salt, right? So lattice enthalpy would describe how much is the strength between the sodium and the chloride ion. And so in case of sodium chloride, it's really strong, right? Because it's not hygroscopic like calcium chloride, but it's pretty strong. And so the lattice greater is the lattice enthalpy, more stronger are the forces in between these two ions. So this was given actually in a chemistry libre text, and I will link that particular article in the description below, but it was really helpful as to how they break down the lattice enthalpy. So what they said was, when you have the force, when you have enough energy, all of these forces are between the sodium and the chloride are broken completely, that they get converted to gases. So when they get to the gaseous state and the ions are far enough away from each other, that energy it took to break it is the lattice enthalpy. So all you need to know is that the lattice enthalpy is giving us the measure of strength of the forces between the ions in an ionic solid. So more is the lattice enthalpy, more is the source. More is the force, stronger is the force. Next one is solvation enthalpy. Now, solvation enthalpy, over here, you have the same sodium and chloride ions. And when you have the water molecule, so this is basically the amount of energy which is released when 1 mole of the salt is getting dissolved in the solvent. So the water molecule is coming in and it is able to break up the force between the two ions, and that energy that is released when 1 mole of the salt is dissolved in the solvent, that is the solvation enthalpy. So for a salt, ionic salt, to get dissolved in a solvent, the strong forces, that is the lattice enthalpy, should be overcome by the solvation enthalpy. So what that is done by making sure that the ion and solvent interactions become strong. So in this case, we can come to these general conclusions. First one is that if the solvation enthalpy is greater than the lattice enthalpy, you will have the salt being dissolved in the solvent. However, if the solvation enthalpy is less in comparison to the lattice enthalpy, basically it is not strong enough to break the forces in between these ions, then you will have an insoluble salt. So it is not getting dissolved in the solvent. First one, solvation enthalpy, if it is more, then this is strong enough that it's able to break the the forces between the ions. It's able to overcome the lattice enthalpy. Similarly, so that'll lead to the salt being dissolved in the solvent. However, when the solvation enthalpy is less than the lattice enthalpy, then it'll be insoluble. So we come to a general idea related to the polarity of the solvents. So in case of non-polar solvents, they have a small solvation enthalpy, and this in turn means that it is not big enough to overcome your lattice enthalpy, right? So this means that in non-polar solvents, our salts are not able to completely or are not able to get dissolved. Similarly, in case of polar solvents, the solvation enthalpy is high enough for it to overcome the lattice enthalpy. So that leads it to become soluble, and so you have this. So I just took an example of oil, which is considered non-polar, and water. Water is a polar solvent, and you have, in this case the salt is not getting dissolved, and in this case it is, right? So that's basically what we are concluding. So based on the solubility of the solvent, there was another very important factor. Temperature also plays a huge role in the solubility of a ionic solid in a solvent. Okay, so for example, if you think about it, when you have a cold glass of water and you're trying to make lemonade, that the sugar takes a bit longer to get dissolved. But if you did the same thing with either room temperature water or warm water, this I guess I shouldn't have taken the example of sugar because it is technically not an ionic solid. Assume it's salt, we're not making lemonade, but if the water is cold, it takes much longer for the salt to get dissolved in water, whereas when it's warm, it gets dissolved much more quickly. So based on so temperature also plays a huge role in solubility of an ionic salt in a liquid or a solvent. So based on the solubility in water, you have the category of ionic salts as category 1, 2, and 3, where they're soluble, slightly soluble, and sparingly soluble respectively. So this I just pulled from your textbook, and this talks about the concentration, solubility, and the concentration, and that's basically how this topic ends. So in this video, all we did was we talked about the two different factors, the lattice enthalpy and the solvation enthalpy. And lattice enthalpy is basically telling us how strong are the forces between, the strength of the forces between the ions, and the solvation enthalpy is the amount of energy that is getting released when 1 mole of the salt is getting dissolved in the solvent. So when you have the solvation enthalpy greater than lattice enthalpy, it is soluble. Solvation enthalpy less than lattice enthalpy, it is insoluble. Similarly, when you have non-polar solvents, the solvation enthalpy is very small, so the salt is not going to be able to dissolve in the non-polar solvent. Whereas in case of polar solvents, with a high enough solvation enthalpy to overcome the lattice enthalpy, the salt is soluble. With that, we're done with this particular topic. In the next one, we're going to be talking about a very important concept called as solubility product.